Hi, this is Brad Strebig. Last time we talked about what happens when we add strong acids to water and how that affects the pH of the solution. In this chapter, we're going to talk about modeling weak acids in natural waters and how that may affect the pH of natural waters as well. To do this, we'll need to understand weak acids and apply some basic mathematical principles and algebra to find our solutions. It's slightly more complicated than the strong acid solution, but can still be very powerful, and in many cases weak acids such as carbonates and sulfates, hydrogen sulfide, and chlorination are all weak acids that we would use this procedure to determine environmental impacts and water quality. Let's start by looking at an example of weak acid solution. Here we have a problem where we have a 0.15 molar solution of an acid HA, which consists of blue and green compounds in solution. We're told that this dissociates 33%. That means 1/3 of the molecules come apart in solution, which seen best represents a sample of the solution after it's diluted with water. So we're given the percentage dissolution of the original solution as 33%. We know also that this has to increase the acid of the solution. So we'll have some increased H plus in solution. Thus we calculate the percent dissociation of each diluted sample and see which is greater than 33%. Take a moment and look at these solutions and see how they differ from one another. Recall that in this solution, the red dots with 3 hydrogen atoms represent the protons, H3O, or also what we've been calling H+. The green and blue dots represent the acid HA that remains in solution in the form of the molecule HA. And the green dots represent the anion or the conjugate base A- in solution once it is partially dissociated. Which of these is partially dissociated by 33%? Take a moment to determine this. So in each case, remember that each unit of H3O is produced from 1 unit of HA, so that we want to find a ratio of H3O to the total amount equal to 33%. When we count on the first example, we have, for section 1, 4 out of the 9 possible components in solution times 100% is equal to 44% dissolution. The next one, we only have 2 ions formed, which is not enough H plus in solution. And finally, because we have a percent dissociation greater than 33%, we have 3 of the possible compounds, 9 possible compounds, diluted in solution. So in this, scene 1 is a dissolution rate that is greater than 3%. The greatest formation of the hydrogen atoms would come from the fraction that dissociates greatest, as shown in part 1. That would be the stronger of the weak acids. So notice weak acids partially dissociate. The more they dissociate and the more they H plus they create in solution, and the more of the anion they create in the solution, the stronger the acid. Scene number 2 only forms 2 H plus and 2 anions in solution. Most of them remain associated in the form HA. Thus, this would be the weakest acid in solution. So we can measure the strength and weakness by the percent that dissociate. Again, when we solve problems for weak acids, we'll write our balanced equations, write the acid equilibrium equation, look at the concentrations, how they change, and solve algebraically, make any assumptions that we can to simplify the algebraic calculations, and typically substitute values into the equilibrium expression to solve for our variable, whatever that may be, and then finally check that the assumptions are justified. Recall that molar concentrations can be represented by the square brackets if we assume an ideal solution. Also, we'll typically assume when we add an acid to solution that since we start with 10 to the minus 7th, unless we've added a very, very small fraction, any significant addition of acid will increase the amount of H3O or H plus in solution to a greater extent than it was there before. This also means that the OH concentration will be small, and oftentimes we can assume that the compound, because it's a weak acid, that the final amount of HA in solution may be approximately equal to the initial amount. Let's start by looking at calculating how we might calculate the acid equilibrium compound for a phenylacetic acid in solution. We'll abbreviate the phenylacetic acid as HPAC. In this case, the phenylacetic acid can build up in persons and create inherited blood disorder that may cause retardation and death. A study of the acid shows that a pH of 0.12 molar HP phenylacetic acid in solution will yield a pH of 2.62. That would be the final pH. And we're asked to calculate the Ka from this value. We need to start by looking at the compounds that can be in solution. We'll assume that most of the acid is from the acid that's added to the water, the phenylacetic acid, and a negligible amount is from the dissociation of H2O. We can also assume, or may also assume, that the final concentration of the phenylacetic acid remains unchanged and is going to be approximately equal to the initial concentration of 0.12 moles per liter, because the phenylacetic acid is defined as a weak acid. Our chemical equation, if we include water in this, will be the phenylacetic acid in the aqueous phase will react with our solute water to form H3O+, or in shorthand H+, either one is okay, plus the phenyl acetate ion in the aqueous solution. Recall that the Ka is equal to the products, the H plus times the phenyl acetic acid ion in solution, over the starting products, which is the phenyl acetic acid. Notice that water again is not in the denominator because by definition the activity of water in solution is 1 because it's the solute. That's our definition of the acid equilibrium constant. Recall also that due to electroneutrality, any H plus that we get in solution will be balanced out by the phenylacetic ion in solution so that they will be equal. Thus, the numerator is simply equal to the square of the H plus concentration. This could also be written as the square of the H3O plus concentration, which is an identical way of writing this, or equal to the phenyl acetate ion concentration squared. All of those statements will be true. We want to note now that the total concentration of the acid in solution is going to be composed of the protonated form of the acid, the HPAC, plus the ion, the conjugate base. The total concentration of the HPAC, when we find the concentration of that, is going to be the 0.2 molars minus the amount of the phenyl acetate ion in solution. Given that the pH was 2.62, the amount of acetate or phenyl acetic acetate ion in the water will be 10 to the minus 62, leading to total concentration for the phenylacetic acid HPAC in solution of 0.117 moles per liter, which is negligibly different, or another way to say that simpler is approximately the same as 0.12. When we put these values, the concentration of H plus 10 to the minus 2.62 squared divided by 0.117, we can calculate the Ka value for our solution. And that turns out to be 4.98 times 10 to the minus 5. If we take another weak acid, such as vinegar, which is formed from the biological decomposition of sugars in water, we can determine the pH of an aqueous solution from adding the weak acid vinegar in solution. The vinegar reacts or dissolves in solution to form the acetate ion CH3COO-, and we'll abbreviate the acetate ion as AC-. If we take the acetic acid and add to 1 liter flask of distilled water so that the total concentration of all acetic acid species is 10 to the minus 4th moles per liter, we want to determine what the pH of this aqueous solution will be. Again, step 1, we define the system boundaries. We write our circle with water, always starting with water, to represent our 1 liter flask, and to this we're going to add some acetic acid. The total amount of acetic acid that we're going to add is 10 to the minus 4. The acetate in solution then is going to form some of the acetate ion, and in this case, because it's a weak acid, we're also going to have some of the protonated form of the acid in solution as well. Since this is a weak acid, it's a pretty good guess that we can start with the HAC concentration equal to the total concentration of 10 to the minus 4. Next, we'll write down all these species in a species list, which is the same as saying this is our variable list. We have H2O in solution. In this case, because it's a weak acid, we have HAC. We also have H+, AC-, and OH- in our solution. Next, we want to write down all the equations associated with the water and the acid in solution. These will be the acid equilibrium constants for water, H+ times OH- equal 10 to the minus 14th, and the acid equilibrium constant for the vinegar, which is H+ times the conjugate base AC- over the protonated acid HAC, and that has a constant value for vinegar of 10 to the minus 4.7 at standard temperature and pressure. So again, we have our acid, and we want to write down other relevant equations, which include the mass balance equation. We know that the total concentration is going to add up of 10 to the minus 4th, and that's going to consist of the HAC and the conjugate base AC-. We also know from electroneutrality that H+ is going to be equal to AC- and OH-. Next, we'll make our simplifying assumptions. First, since we've added an acid to the solution, it's probably likely that the base concentration, OH-, is going to be approximately 0, or negligible, since we've added the acid. This allows us to simplify the electroneutrality equation so that H+ is equal to AC-. Now we can take these terms and substitute them into our acid equilibrium constant and solve algebraically for this solution. Writing down the acid equilibrium constant and making our substitutions, here we've substituted AC- for H+, gives us a Ka value equal to AC- or H+ squared over HAC times 10 to the minus 4. If we rewrite this in a linear fashion, we have HAC is equal to AC- squared over 10 to the minus 4. Here we have a squared term, and we can write the denominator in terms of HAC. So our total concentration is HAC, which is equal to AC- squared over 10 to the minus 4. So notice we start on the left-hand side of this equation with the same mass balance equation we begun with. The total concentration is equal to 10 to the minus 4. That's equal to the HAC plus AC-. The HAC we've determined algebraically from our acid equilibrium constant is going to be equivalent to the conjugate base concentration, the acetate ion squared, over 10 to the minus 4 by rearranging the acid equilibrium constant. We've substituted that into our mass balance equation, so that term plus the AC- is going to equal 10 to the minus 4. When we multiply these terms out, we have a squared equation with one variable. That 10 to the minus 4.7, when we multiply, it will be 10 to the 4.7 times the square of the acetate ion plus the acetate ion minus 10 to the minus 4 is equal to 0. This has the form of a quadratic equation. We can put this into the quadratic formula for the quadratic equation and solve for the concentration of the AC minus. Recall from electrode neutrality that that's equal to the hydrogen ion concentration as well. Substituting in the parameters, where A is 10 to the 4.7, the variable B is 1, and the variable C is 10 to the minus 4 in our quadratic equation solver. You can solve this on your computer or on your calculator, whether it's programmable in Excel or just pushing all the buttons by writing out the quadratic equation. When that's done, we get a value of H plus equal to 3.6 times 10 to the minus 5 moles per liter. Recall that we wanted to find out the pH of the solution and all the ions dissolved species in solution so that the concentration of the HAC, the total concentration, 10 to the minus 4, minus the concentration of the AC minus, gives us a value of 6.4 times 10 to the minus 5 moles per liter for the concentration of the HAC. We want to check and make sure that the hydroxide ion concentration is relatively low. We can find the hydroxide ion concentration from multiple avenues, but one method is from the water equilibrium equation. So the hydroxide ion concentration is equal to the water constant, 10 to the minus 14, divided by the concentration of protons, H plus in solution, which we previously determined was 3.6 times 10 to the minus 5. 10 to the minus 14 over 3.6 times 10 to the minus 5 gives us a value of 2.8 times 10 to the minus 10, which is much, much less, approximately 5 orders of magnitude less than 3.6 times 10 to the minus 5. Thus, our assumption that the OH minus was negligible is valid, and we can accept that assumption. Finally, we're ready to determine the pH, which is equal to the negative log of the hydrogen ion concentration minus the log of 3.6 times 10 to the minus 5, or the pH of the 10 to the minus 4 vinegar solution in water is going to give us a pH of about 4.4 in solution. This method can be applied, this general procedure, to any weak acid and base problem to give us a powerful tool for calculating pH in solutions and possible environmental effects, which will be discussed in the next section.